right. So A3, right? So A3 now um, is another reaction, enthalpy problem. Sorry, right? And thinking, well, actually, no, this isn't an enthalpy problem. This is a work problem, but kind of going over like gases and all those different relationships. So if we're, looking at it, right, first thing is balance the reaction. So if we're balancing this reaction, right, to form ammonia in this case, right, so we have NH3, right, we have, N2, H2, NH3, right? So if we have one thing of N2, right, that means that we're going to have two of NH3. So if we have two of NH3, that means we have to have 6 hydrogens. We'll only have 2 right here with the H2, right? So that becomes 3. And so, right, that right there becomes the balanced equation in this case. Right. And so now the question is, right, is kind of like more of a thinking problem, is like, what does the system look like, right? What do the surroundings look like? And so, in this case, right, we have just simply, essentially a box, where we have, our molecules, right? And so inside of that box, right, we're just simply going to, before the reaction happens, right, there's just simply going to be 4 gas molecules that are going to be hanging out in there, right? Or at least a ratio, right, of 4 gas molecules, right? So you can draw it that way. You can also, right, have it be H-H and so forth, and however you want to, right? And so this is going to be the system, right? And then this right here is the surroundings. And so then after the reaction is done, right, what happens is that now, instead of having 4 gas molecules, right, you're only going to have 3, but they're going to be more complex. Or sorry, 2, right, where you're forming these guys. And so there's a net change in the number of moles of gas, right? So in terms of the mass of gas, that's going to be exactly the same. But the number of moles of gas is going to be different. And that becomes important for gases because when we're talking about gases, right, we talk about moles of gases, and that has an influence on the pressure and the volume and the temperature, of the system compared to, a mass of gas that has nothing to do with, directly with any of those. In those cases, right, that doesn't, influence the pressure, the volume, or the temperature, right? It changes the density, right? But it doesn't change the volume, right? Because the volume is, completely dependent upon, the gas laws in those cases. And so, if we're looking at this right here, right, and we're assuming that we're at a constant pressure of 1 atmosphere and an atmospheric temperature of 25 degrees Celsius, right? The question is, do we expect the volume to increase or decrease? And so if we just simply look at, the ideal gas law, so we have PV equals nRT, right? So we know that the number of moles of gas are going to change, right? So we know then that we're going to have delta nRT, right? Because there's a number of moles of gas that change. And so we also know that P stays the same. And so that means then, though, that the volume has to change, right? So we have P delta V in this case. And so, in this instance right here, right, that's what the, equation is that relates the two of them with each other. And so, because temperature is constant, R is, the gas constant that stays exactly the same. The pressure stays exactly the same as well, right? So the volume has to change. Now the question is, does the volume go up or go down? And so the way that we can relate that, right, is if we look at, what delta N is equal to. So a delta N, right, initially, or, the final amount, right, is we're only going to have 2 moles of gas, right? But initially we had 4 moles of gas. And so that means then, right, that delta N is equal to negative 2 moles in this case. So if the number of moles of gas decreases, then that means that the volume has to decrease as well, in this case. All right, and so that's why those have to go down. Right, and that's the direct relationship that you have right there. So now the last part of that question, right, calculate the work in joules performed in the formation of 20 grams of NH3 gas at 1 atmosphere and an atmospheric temperature of 0 degrees Celsius. Right, and so what we can do in this case right here, first things first, right, it doesn't matter what the mass of ammonia is that we form, it's the number of moles of ammonia that we're forming in these cases. So if we go through, the first thing we want to do is we want to calculate the number of moles. So N of ammonia, right, is going to be equal to the mass of the ammonia divided by the molecular weight of ammonia, right? So the mass is 20 grams. And so we divide that by the molecular weight. And so that's going to be 14.01 plus 1.01 times 3. That comes out to 17.04 grams per mole, right? Grams cancel, mole goes up top. What we get is 20 divided by 17.04 comes out to 1.17 moles. Right, so that's how many moles of ammonia we're forming in this case. So using what we know from the balanced equation, right, the relationship that we have is that, that's how many moles of ammonia we have, right? So then that means that for the number of moles of N2 is going to have to be then, half of that, right? Because the relationship that we have is, right, for every 2 moles of ammonia formed, right, we have to use 1 mole of N2. So that comes out to being 1.17 divided by 2. So that's 0.585 moles, right? And then the number of moles of H2 that we have in this case, right, is going to be a relationship of, for every 2 moles of ammonia, right, you have to use 3 moles of H2, right? So we have to then multiply 1.17, right, by 1.5. And so 1.17 times 1.5 comes out to 1.755 moles. Excuse me, right? So we have this right here, right? And so now what we can do is we can calculate what delta N is. So delta N is equal to 1.755 moles plus 0.585. Oh, wrong way. Sorry, because it's final. The final amount is 1.17 moles, right? Minus, and then now we have 1.755 moles plus 0.585 moles, right? And so what we get then for delta N is 1.17 minus 1.755 plus 0.585 comes out to being negative 1.17 moles, right? Right, and so that's what our delta N value is. Now, when we calculate work, right, at constant pressure, right, the equation that we use for work is equal to negative P delta V, and so what we can do, right, we can calculate directly what delta V is, but we don't have to go through that process, right, of calculating what V was initially and what V is final, like at the end, right? We can just simply use our delta N values in those cases. And so, right, because we already have this right here, that relationship that we had developed, right, where, we know that P delta V is equal to delta nRT, we can just plug that into our work equation. So now what we have is negative delta N RT, right? So that works just as well in this case, right? And we've already calculated what delta N is. We know what R is because it's the gas constant, right? And we want to use the one that has joules in it. And we know what the temperature is, right? We're at 25 degrees Celsius. One important thing, right? You want to convert that into Kelvin, right? And so we now can, we can plug in all the values that we have. So we have negative 1.17 moles. Right, we can have R, which is 8.314 joules per mole Kelvin, right? And then we have our degrees, right? So 25 degrees Celsius, right? We add 273 to that. 25 plus 273 comes out to 298, right? So that's 298 Kelvin. Wait a second. Did I use a different? I used a different value on the answer key then here, let me just double check. Again, this goes back to the mistakes that I made with not paying attention to my versioning of things. This is A3. Okay, yeah, we did it at 0 degrees Celsius here. So my answer key, the problem is off. I just need to fix that on the key. That's easy enough to fix because it's just the problem that's wrong. But like, yeah. All right. So this should be 0 degrees Celsius. Right. Or actually, wait, that's 0. This is 0 as well. I'm looking at the wrong things, right? So we're talking about 273. Sorry. Oh yeah, no, all that stuff's correct. Okay, ooh, I thought I was off on something. I was just looking at the wrong part of the problem because I was, whatever. Anyways, okay, right, it's 273 Kelvin is the temperature we're at, right? Because we're at 0 degrees Celsius in this case. So we have that. So now we just plug all of that in. Excuse me, work is negative 1.17 times 8.314 times 273 Kelvin comes out to 2,660 joules, which I believe is what I have. Yeah, 2,000 on the key. I put down 2,663 joules, right? That's what I have matched right here, right? So the original answer that I had on the key that I think I released on Tuesday, right? I think was like 29,000. So that was the scenario then where I had actually used the 25 degrees Celsius, right? Because if we just go through and we do that times 298, right? That whole thing, right? That comes out to 2,900 joules in that case. So, always pay attention to what this that specific problem happens, and what those conditions are in those cases. And so, yeah, I mean that was one thing. Some people that had talked to me in office hours, right? Because some of the Chem 101 problems, they switch up what they look like very similar problems, and they have slightly similar values, right? But if like one of the values is like off, right? If you go from like 1 liter to 2 liter, that's going to dramatically change what the final, answer is going to be in those cases, right? So you always want to make sure that for a specific problem, you're always looking at what that problem is actually giving you as your condition. So that's always, an important lesson and an important thing to do. But yeah, so I mean, so that's how you work your way through A3, right? So the easiest way to do it, right, is because temperature stays constant, right? Pressure stays constant. The only thing that's changing is the number of moles, right? And that relates directly to the change in volume. You can do a similar thing, right, where I could say, if you change the temperature of the system, right, and the pressure stays constant, and the number of moles of a gas stay constant, right, the volume's going to change, right? And so there's some type of work that is going to happen in those scenarios too. But yeah, depending on, the conditions in those cases, right, will then also dictate what's going on. Anyways, all right, so that's A3.